Welcome to a new session on the massive open online course Introductory Concepts of Digital Computing offered by Swayam. During the last two classes, we were discussing on Boolean algebra. In this session, we study about the electronic circuits that help to implement the basic functions of Boolean algebra, logic gates. We know that computer is an electronic device that performs different arithmetic and logical operations. How does this machine carry out these operations? The answer is using digital circuits. These circuits are designed using logic gates. Logic gates are the basic building blocks of a digital circuit. Here we deal with the basic logic gates and truth tables. Also, we learn to design logic circuits using basic logic gates. Logic gates. In a computer, information is stored in the form of binary signals, that is, either in the form of 1 on or high state or 0 off or low state. This binary information or binary signals inside a digital system is manipulated by logic gates. Gates are physical components or hardware that produce a binary signal 1 or 0 to a set of binary inputs that satisfies a logical requirement. Variety of logic gates are used in digital circuits, and we are going to learn only the basic gates today. There are 8 basic logic gates, and all other logic circuits are designed using these gates. They are AND gate, OR gate, NOT gate, buffer, exclusive OR, exclusive NOR, and the universal gates NAND and NOR. Only some of the important gates are going to be described here. That would be sufficient to introduce the concept of logic circuit design. Let's see the AND gate. The first logic gate we discuss here is AND gate. It is used to realize or implement logical multiplication. It is one of the basic logic gates. AND gate can have more than one input signals and a single output signals. The output of AND gate is 1 if all of its inputs are equal to 1. Otherwise, if any of the inputs are 0, the output is 0. See the logic diagram or graphic symbol of an AND gate. This gate has two inputs A, B and a single output X. Inputs are drawn on the left and output is on the right side of the symbol, and we follow the same approach in all the cases. For a two-input AND gate, when both inputs A and B are high, output X is high. When either A or B is low, or when both A and B are low, X is low. It is nothing but logical multiplication, right? So, a high output or 1 is produced only when all the inputs are high. The output is low or 0 otherwise. Hence, an AND gate can be used to determine when certain conditions are true at the same time. The output 1 indicates that they are the same. Otherwise, the output will be 0. The behavior of a gate can be represented conveniently using truth tables. How to generate the truth table for the AND gate? Let us consider a two-input AND gate. First of all, list all input combinations for A and B in the first two columns, and after, write the corresponding outputs in the third column. Each column must be labeled appropriately, and also make sure that an n input AND gate truth table has 2 raised to n input combinations. See the truth table. The inputs A and B take the values 0, 0, 0, 1, 1, 0 and 1, 1, and the output are 0, 0, 0 and 1 for each input. So, for an AND gate having two inputs, the number of input combinations will be 4. For 3 inputs, the number of input combinations will be 2 cube equal to 8. For 4 inputs, the number of input combinations will be 2 raised to 4, that is equal to 16. Also, let me remind you the Boolean expression for a 2 input AND operation. It is x equal to a dot b, or we say x equal to ab. We can either use a dot between the variables to represent the AND operation, or concatenate the variables without an operation symbol between them. The applications: AND gates are used to design many combinational and sequential circuits like adders, flip-flops, decoders, multiplexers, etc., which we will be dealing in the later sessions. The particular behavior of AND gate helps to control a device by allowing or not allowing a signal from one point to another depending on certain conditions. It is also used in the designing of alarms. The next is OR gate. The next topic of study is OR gate. It is the physical realization of Boolean addition operation or logical OR operation. This electronic circuit produces a 1 or high output when any of its inputs are high, and if both inputs are low or 0, then the output is low or 0. The logic diagram describes an OR gate for 2 input signals. Here the output is 1 if input A or input B or both inputs are 1. Otherwise, the output is 0. That is, if any of the inputs are 1, an OR gate produces a high output. Then we can generate the truth table as shown here. For 0, 0, x equal to a plus b, that is the output will be 0. For 0, 1, it is 1, 1, 0, 1, 1, 1, the output is 1. As in case of AND gates, we can have more than 2 inputs for an OR gate too. Let's consider a 3 input OR gate. The input signals are A, B and C, and the output is represented by x, which is equal to A plus B plus C. We can write the truth table for this OR gate. Give 3 inputs in the first 3 columns. The last column gives us the output. Now observe the output column. Only the first row results with 0. As all its input signals produces 0, all other cases produce a high or 1 output signal. Here you can see from the second row till the last we get 1 output, but in the first row all inputs are 0 and the result is 0. Similarly, we can also have truth table for a 3 input AND gate. See the table here. For the first 7 rows, the inputs contain 0 values and the output is 0, and for the last row the inputs are 1, 1, 1 and the output is 1. Observe the results. An AND gate has a 1 output when all of its inputs are 1, whereas an OR gate has a 1 when any of its inputs are 1. The applications are: OR gate is used in the design of multiplexers and many other arithmetic and logic circuits. OR gates are used in the design of temperature detectors. The next is the inverter or NOT gate. How to implement the logical operation complementation? Here the output signal must be the reverse of the input signal. The logic gate that inverses its input is NOT gate. It is also called as inverter. Just recall the complementation operation in Boolean algebra. You may remember it is a unary operation. That means it is operated upon a single variable. So here a NOT gate also will have only a single input signal, and if the input is high or 1, then the output will be low or 0. If the input is low or 0, the output will be high or 1. Logic diagram of NOT gate is drawn here. The truth table for NOT gate describes its behavior. When input A is 0, output X is 1, and when A is 1, the output is 0. It is given in the truth table. For A0, x is 1 and A1, x is 0. When we write a logical expression for NOT operation, the inverter or the complement is represented by a bar or prime. In the same manner, a small circle in the output of any of the graphical symbol represents the complement or the inverter function. Let's have a detailed discussion on this in the next session. What if we give two cascading inverters like this? This is nothing but double complementation. For an input signal A, the output signal will be A double complement, which is again A itself. Any logic operation can be inverted by using NOT gate. The NOT gate is used to find the complement of any digits, which is used in binary subtraction. It is used to deactivate any operation by giving an inverted signal. NOT gate or the inverter is used in the design of NAND, NOR gates and many other arithmetic and logic circuits. The next topic is logic circuits. Normally, we use logic gates in combination with other gates to build logic circuits. Logical expressions can be derived for any given circuit by progressing step by step on its gates from input to output. Let's see how to produce a Boolean expression from the given circuit. Here we have three inputs A, B and C. In this logic circuit, input A and B is fed to the AND gate 1 and it outputs A dot B. Similarly, input B and C is fed to an OR gate, that is gate number 2, resulting B plus C. The AND gate number 3 receives two inputs B and C and produces B dot C. So, after the first level, we are with three logic functions A dot B, B plus C and B dot C. The outputs from gate 2 and gate 3 are again fed into an AND gate, which is numbered as 4, generates the function B plus C dot BC. Finally, the OR gate, that is number 5, produces a sum by using its inputs AB and B plus C dot BC. Hence, the final logic expression is AB plus B plus C dot BC. I will make it clear by giving one more example. Please concentrate on the circuit given here. In this circuit, we have three inputs A, B and C. All three inputs are fed into the first AND gate and it produces the output A dot B dot C, or we can call ABC. Then the inputs B and C are complemented using inverter gates and combined with the OR gate to perform logical OR operation to get the result as B complement plus C complement. When we proceed to the third gate, we have two inputs. One is A and the other is the output of gate 2, OR gate. In turn, the OR gate, that is the logical gate numbered 4, receives two inputs ABC and A dot B complement plus C complement, and it generates the final Boolean expression ABC plus A dot B complement plus C complement. So far, we were discussing on the method of deriving a Boolean expression from the given logic circuit. How about the reverse problem, creating a logic circuit from the given Boolean expression? We know that the three gates AND, OR and NOT are sufficient to implement any logic expression. So, now we are going to construct a logic circuit using these three gates. How do we design logic circuits for the Boolean expressions? Let's consider an example AB plus CD. The expression is the sum of two product terms AB and CD. AB is A and B, and AND gate with two inputs A and B results in AB. Similarly, CD is C and D, and AND gate with two inputs C and D results in CD. The two product terms are ready now. Then we OR the output terms by using an OR gate. When you have the Boolean expression, building the circuit is very simple. Let's take another example. The function f is equal to ABC complement plus BC complement plus AB complement. By looking into the expression, we are able to write the logic circuit. The expression is given in sum of products form. So each term can be realized using an AND gate. All outputs from AND gates are connected to OR gate will give you the circuit. In each term we have a complemented literal. Either you can use the input variable as a complemented variable like B complement or C complement, or use an uncomplemented variable and let it passes through an inverter to obtain the complement. So here we use 3 AND gates to bring about the product terms, and they are logically ORed using the OR gate to achieve the final expression A B C complement plus B C complement plus A B complement. Suppose you are requested to construct a circuit from the truth table instead of expression. How do you develop a circuit if the expression is not given? One method is to use the canonical form, sum of products expression. Let us do one example on this type of problem. Look into the truth table given here. The input values are A, B, C, output is X, and for few of the input values the output is 1, and it is noted down. For the input 0, 1, 0, the output is 1, A complement B, C. For the input 1, 0, 0, the output is 1, that is A, B complement C complement. For 1, 0, 1, it is 1, that is A, B complement C. And the next 1, 1, 0 input combination and its corresponding minterm is A, B, C complement. So this truth table tells us the behavior of the circuit we are going to implement. Each one in the last column notifies the input combination that gives a true value for the circuit. So let's select all the rows that outputs a value 1 from the given table. So the sum of products expression will be A complement B C complement plus A B complement C complement plus A B complement C plus A B C complement. Now we can create the logic circuit easily by using AND, OR and NOT gates. Draw 4 AND gates for 4 terms, then connect inputs required for each gate. We have given 3 inputs A, B and C. Draw the input lines from A, B, C, and also you can draw the complemented lines by using inverters. Then draw 4 AND gates for product terms. Connect each AND gate with corresponding inputs. After that, we have to connect it all the outputs from AND gates with an OR gate to get the final expression. It is the logic diagram for the function A complement B C complement plus A B complement C complement plus A B complement C plus A B C complement. Can we minimize this expression? A complement B C complement plus A B complement C complement plus A B complement C plus A B C complement. Yes, when we minimize, we get the expression as A B complement plus B C complement. The expression is A complement B C complement plus A B complement C complement plus A B complement C plus A B C complement. The middle two terms has a common factor A B complement. You can take it out. Then we get A complement B C complement plus A B complement into C complement plus C plus A B C complement. So the expression will become A complement B C complement plus A B complement plus A B C complement. You can rewrite the terms A B complement plus A complement B C complement plus A B C complement. Again, in the last two terms we have common term. Take it out. So we get A B complement plus B C complement dot A plus A complement, which is equal to AB complement plus BC complement. This is the minimized expression. It is the same expression that we did last. See the difference? The number of gates are reduced. Also time and space. So your circuit gets simplified when you minimize the expression. Before concluding, let's have a glance through two more logic gates. They are Exorgate and Exorgate. The exclusive OR gate or Exorgate. A combination of AND, OR and NOT is sufficient to represent the function of exclusive OR gate and exclusive AND gate. But these gates play vital roles in building up certain applications and so treated as basic logic gates. They also have their own unique symbols. The exclusive OR gate, in short we call Exorgate, produces 1 if only one input signal is 1. The output is 0 when all the input values are either 0 or 1. In other words, we can say that the output of Exorgate is 1 if inputs are different and the output is 0 if the inputs are same. The logic diagram of the Exorgate is shown here. A and B are the two inputs, X is the output. The logical expression for Exorgate is X equal to A complement B plus A B complement. The XOR operation can be represented using an encircled plus symbol. The output values for various input combinations are presented in the truth table. For the inputs AB 0 0, the output is 0, and for the next two cases, when A and B are 0 and 1 or 1 and 0, the result is 1, and in the last case, when A is 1 and B is 1, the result is 0. Now let us see how to realize an XOR function using AND, OR and NOT gates. The desired expression is A complement B plus AB complement, which is a sum of products term. So for each product term, we require an AND gate. A complemented literal can be generated by a NOT gate. So we get the two terms A complement B and AB complement. Finally, a logical OR operation is performed on all the output signals generated from AND gates. Thus, we get this circuit. Next is exclusive NOR or XNOR gate. The next is exclusive NOR gate. In short, it is called XNOR. XNOR gate is the complement of exclusive OR. The output of this gate is 1 only if both inputs are equal to 1 or both inputs are equal to 0. XNOR gate also has a unique symbol, which is a bubbled XOR gate. The bubble indicates negation. In this logic diagram, A and B are the two binary inputs and X is the output. Logical expression for XNOR gate is X is equal to A complement B complement plus AB. XNOR operation is represented using an encircled AND operator. We can create the truth table from this expression. When both A and B are 0, the output is evaluated as 1. When A is 0 and B is 1, or when A is 1 and B is 0, the result is 0. If A and B are 1, the output is 1. That is, it will give an output 1 if both inputs are same and an output 0 if inputs are different. See the truth table 0 0 1 0 1 0 1 0 0 1 1 1. The XNOR function can be implemented using the AND, OR and NOT gates. The logic circuit explains the same. The first AND gate produces the term AB, and the second AND gate with the combination of inverters gives the next term A complement B complement. These two terms act as input to the OR gate, and thus we obtain the XNOR function AB plus A complement B complement. Let me summarize the topics we discussed. In this session, we have considered the basic building blocks of a digital computing device, logic gates. Logic gate is an electronic circuit that receives one or more input signal and generates an output signal. We discussed about 5 basic logic gates: AND, OR, NOT, XOR and XNOR, their logical diagrams and truth tables. Also, we learned how to realize a Boolean function using these gates. The logic gates were combined by connecting outputs of some gates to inputs of other gates, and thus we created logical circuits. We were also able to derive Boolean expression from the given circuit diagrams. Let's explore more on logic gates, specifically the universal gates, in the next discussion. Thank you for watching. See you in the next session. Bye.